Hello students, welcome to the next session. So we will move on with the next module, module 5. So in this session we will be discussing about DC to AC converters, which are also known as inverters. So we have a brief idea about inverter circuit. Inverter means it which converts DC power to AC power, right? So the at the output, the voltage may be voltage and frequency at the output would be the desired one, which will be AC. So this AC output, we can control it. It can be fixed or variable. So we know how to control that. We have observed and studied in the previous converters that the output can be controlled by the um, turning on and turning off of the power semiconductor device, which are using as switches in the circuits, right? So similarly in the DC to AC converters as well, in the inverters you'll be using the semiconductor devices like BGT, MOSFET, IGBT, MCTs, SITs, GTOs, SCRs popularly, right? So um, as we know, the uh, output voltage waveform of the at the output, it depends on what type of power semiconductor device you are using, right? So ideally for very high power outputs, generally the thyristors or the SCRs will be used. So since in this session, we will be first discussing their different classification, that is inverter classification, and simple half bridge inverter. It's working with the R load. Okay. So by the end of this session, you will be able to describe the operation of single phase half bridge inverter with R load. So as I mentioned, the DC to AC converters, which are also called uh, inverters, as we know, they are popularly used wherever you want the load to be, the voltage at the load to be AC, right? So obviously the input for such circuits will be the fixed DC source. So the fixed DC source will be used to convert it to the load which is requiring the AC type. Okay. So popular applications where you can imagine where these inverters come into picture will be as listed here: variable speed AC motor drives, or induction heating, or aircraft power supplies. Obviously you cannot go for a AC slot there, so you will need a battery to power up the aircraft. Obviously the UPS, what we are familiar with, then high voltage DC transmission lines, then battery vehicle drives, then regulated voltage and frequency power supplies, etc. Okay, so these are the a very brief and broad application list that is shown here, just to give an idea about DC to AC converters. So based on different ways that are these circuits that are designed, based on that the inverters can be classified according to the output, according to the source. Okay, so we'll just brief like what are the different types of inverters here. So as you can see, based on the output source and type of load, first category is according to the output characteristics. So you have the inverters that can be classified as square wave inverter, or sine wave inverter, or modified sine wave inverter. So as the name clearly indicates, at the output you will be getting a square wave. Yeah, so square wave inverter will produce a square wave AC voltage of a constant magnitude. Okay, so the output of this type of inverter can be only varied by controlling the input DC voltage. All right. So the square wave AC voltage of an inverter, such type, it is used only where you have the applications where low or medium power requirement will be there. So such in such situation, square wave inverters will be used. However, the second type, sine wave inverters, as the name indicates, the output will be, at the output the voltage will be sine. Okay, so sine wave output voltage, which is ideally suitable for very high power applications. Okay, so in order to get sine wave, we have to go for using filter circuits, like, because obviously uh, at the output, if you are going for smoothening this square wave, which is having, say, harmonic components, to remove these harmonic components, obviously you have to go for filters. So when you remove these harmonics, you will get a smooth curve, which you will end up with sine wave, right? So when you use filter circuit, so these filters, whatever you're using, should be capable of handling large power. Okay, so for such situation, the cost and weight of the inverter would be going up, because the filter, what you need for having a smooth sine wave at the output, the filter circuit will be of should be of high capability to handle large power. All right. So yeah, next, according to the source, the inverter can be classified as voltage source inverters or current source inverters. So in voltage source inverters, the input to the inverter is provided by DC voltage source, whereas in current source inverter, the voltage source is first converted to current source and then applied uh, to the inverter circuit to provide the power required. Okay. In the next category, that is, as we say, we are using the power semiconductor devices, like, as I mentioned earlier, popularly the thyristors will be used for high power applications, right? So based on the thyristors, how the thyristors are used, according to that, again, the inverters can be classified as according to the method of commutation of these thyristor circuits and according to the connections. Okay, so classification according to method of commutation. As we know, commutation process, there are two types: line commutation and forced commutation. So based on that, the thyristor circuit, how it is turned off, commutation means turned off, right? So how they are turned off, based on whether it is line commutation method or forced commutation method. Based on that, inverters, the relevant inverters are called the line commutation inverters and forced commutation inverters, based on the type of commutation circuit that is used for the thyristors or the SCRs. Okay, then yeah, then according to the classification, that is classification according to the connections of these thyristors, the inverters can be classified as series inverters, parallel inverters, and bridge inverters. So based on how are you using these thyristors or SCRs in the circuit, whether it is the connection is in series type, parallel type, or you're arranging the SCRs in a bridge fashion, based on that, the inverters are again classified as series, parallel, or bridge inverters. So in bridge inverters, you again have half bridge inverter and full bridge inverter. So in this session, as I mentioned earlier, we will uh, go through the basic working principle of single phase half bridge voltage source inverter. So obviously, as the name indicates, It is single phase, half bridge. Half bridge means the configuration of the SCRs used is in the bridge fashion, and it is voltage source inverters. That is, at the input you have voltage source that is feeding as the input to the circuit, right? So the basic method how we go for this inversion process or inverter operation. So imagine here the simple way of understanding things will be, you are already familiar with DC to DC converter, right? So in DC to DC converter, what do we do? The conversion, that is the output at the DC, how are we converting the average output at the load? We are controlling by the duty cycle of the switches in the circuit, right? So by controlling the duty cycle, that is the time duration at which the switches are kept on and off, yeah, based on that the output is controlled, whether you are going for a step down or step up operation, right? So the same basic principle, DC to DC converter is a basic operation in power electronics, that is converters. So the based on the DC to DC conversion, all other converters can be understood clearly. Okay, so imagine to get DC to AC conversion. So what do we do there? Connect the load across the DC source for, say, for certain duration of time. Imagine you are connecting the source to the load to the load to the source for, say, for 10 milliseconds. Okay, that means what? Your load is getting your source, say, only for 10 milliseconds, right? Then reverse the connection of the load, okay, and connect it for a time duration of 10 milliseconds again. That means at the load you are getting negative voltage of the DC source, right? So negative voltage for time duration 10 milliseconds. So then what can you expect there at the output? You may expect the output at the load, you will have positive voltage for 10 milliseconds and negative voltage for 10 milliseconds. So for one complete cycle, you will get a square wave at the load. I hope you are able to uh, visualize what I'm explaining here. Okay, at the load, you will be getting positive voltage for 10 milliseconds and negative voltage for 10 milliseconds when you connect the load in a across the input for 10 millisecond and reverse the voltage, reverse the connection and connect the load for another 10 milliseconds. So what can you expect at the output? You will expect a square wave for a period of 20 milliseconds, right? So which, if you are repeating this connection, yeah, repeating continuously, then you can expect a square wave of 50 hertz. Okay, 50 hertz square wave can be generated at the low. Obviously there will be harmonics which can be removed by using filter circuits, right? So this is the basic principle or basic um, uh, fundamental operation, what you can use it to understand DC to AC conversion. So let us go ahead with this. So here is the circuit, single phase, half bridge inverter. So here the single phase doesn't give any relevance in terms of the input. The single phase is because the term single phase is because of the voltage what you can observe at the output, the load. Okay, so, and as I said, it is a bridge configuration. So the switches what you are using here is T1 and T2, and at the input you are using a 3-terminal DC supply. Okay, so the switches S1 and T1 and T2 are the gate commutated devices. It can be BJTs, it can be MOSFETs, GTO, IGBT. Here thyristor is shown. So T1 and T2 are used. Okay. So when these switches are closed, there is a conduction. That is, the devices will conduct when they are turned on or they are fired, allowing the current to flow through in the circuit. Okay. So to understand the working, we can divide the circuit operation into two periods. Say in the period 1, where only one first switch, that is T1, is say conducting for time duration 0 to T by 2. Okay, imagine T1 is turned on for time duration between 0 to T by 2, and in the next period, period 2, the T2 device will be conducting for time duration T2 T by 2 to T. Okay, let me see. Okay, here I'm just showing you in the waveform here. Say this point can be T by 2 and this is T. So the total time period, right? So for 0 to T by 2, say your first device T1 is conducting and T2 is conducting for the next time slot, that is T by 2 to T. Okay, so observe what happens. As I mentioned earlier, the where T is 1 by F, that is F is the frequency of the output voltage waveform. All right. So as I mentioned earlier, at the input you have the 3-terminal DC source. All right. So see here, the first terminal is connected to this network, that where your first switch T1 is connected. The second terminal is connected to the second switch T2, and the third terminal is connected to load here. Okay. So this is the bridge circuit. The role of D1 and D2 comes into picture only when the load is not only resistive. So when the load is resistive, D1 and D2, this is D2, sorry. Okay, so I was mentioning D1 and D2 comes into picture only when the load is RLC type. So that is when your load has inductance or capacitance. Only then the D1 and D2 will come into picture, which will be used to reduce the damped current in the circuit. Okay, so because we know that whenever the load is inductive or capacitive type, the current will lag from the load, from voltage, the output voltage, right? The output current will be lagging with respect to the output voltage. So that lag is nothing but what we call it as the damped output or the damped current that is flowing in the circuit. So to avoid or to control that, D1 and D2 will be used. Okay. So when we are discussing RL load, we will be discussing about D1 and D2 and its role. So right now, for resistive load, D1 and D2 has no role. Okay. Since it is a popular way of having the circuit, here it is shown. All right. Now observe here what happens when the input, the DC input, what you have Vs, it is split, that is into two parts. So the first is connected to the switch T1 and the second half of the input is connected to the second switch. Okay, so when T1 is conducting, as I mentioned, between the time duration 0 to T by 2, so the current will be flowing in this circuit, right? In this circuit where T2 is off there. So the input what you have applied here will be appearing at the load, right? So at the load you will have positive Vs by 2. So since the circuit current will be flowing in this direction, so here it will be positive and here it is negative. The load will have the voltage positive at this terminal and negative at this terminal because of the switch T1 conducting between 0 to T by 2. Okay. Now imagine you have turned off T1 and you have turned on T2. So the conduction of the circuit will be in this direction, right? So T2 is now turned on, means it is acting as a short circuit. So current will flow in this direction. So observe here, you have Vs by 2 connected here. So since the current is flowing in this direction, the voltage across the load will be positive here and negative here. Okay, so imagine the fundamental operation principle I had mentioned earlier. In order to get the AC output from the DC source, what do you have to do? You have to simply connect the load in say one direction and reverse it for another direction for different time period, right? So that is what is happening here using this bridge circuits. So when T1 is conducting, the current in the circuit will be flowing in this direction and the voltage across the load will be positive here and negative here, right? When T2 is conducting, the current in the circuit will be in this direction. So at the load, the voltage across the load will be positive here and negative here, right? So when you observe the output across the load, so you will be getting alternative input what you have applied here. Okay, let us understand that in the waveform here. As you can, it is shown here. So IG1 and IG2, I hope you are familiar. It is the gate triggering signal that is applied to thyristor 1 and thyristor 2, right? So it can be a single pulse, a small spike to turn on the thyristor, or it can be a pulse, right? So when during this duration, when IG1 is applied, so obviously T1 will be conducting. So when T1 is conducting, the output, what you can observe here is positive Vs by 2. Okay. In the next time slot, that is here it is T by 2 and it is T here. In the next time slot between T by 2 and T, when you are applying IG2, that is the gate triggering pulse for the thyristor 2 will be conducting here. So observe here, the output will be minus Vs by 2 according to the circuit explanation what we had just now, right? Okay, so the output here is reverse. So if you are continuing like that, next you trigger the T1, T1 will be conducting, so output at across the load will be Vs by 2. Then when T2 is conducted or fired, the output will be minus Vs by 2. So what you are getting is a square wave, yeah, square wave which is oscillating. So it is nothing but the AC square wave, square output voltage what you are getting at the load. So as I mentioned, this type of AC output voltage can be used for applications where you need a very low or medium power applications. Okay, so if you want to go for a very high power applications, then the AC what you should be expecting should be sinusoidal. So to get the smooth sinusoidal curve, obviously we know we have to go for filter circuit to remove the harmonics in this output what we have here, right? So there will be a lot of harmonics. So that has to be removed to get a smooth curve, right? So that is about the basic operation of single phase half bridge voltage source inverter. So mathematical expression of this, that is the RMS output voltage, instantaneous output voltage and current, will be discussed in the next session.